Welcome to the video solution of your selected question from the Mathematics the Easy Way DVD. If you have not yet seen the introduction video on the DVD, please do so now, as it outlines how the Easy Way series will help students to be successful in their CXC exam. While the Easy Way video solutions will help to cement the understanding of certain special questions, the solution books are still absolutely necessary as they cover all the various types of questions that are set in CXC exams.
We are now at question 11, the last question of this CXC CSET June 2013 General Paper 2 exam video solution. And in this question we are presented with this vector triangle, and we are told that the vector OA, the position vector of A, is 2A, and the vector OB, which is the position vector of B, is 2B. We are also told that the point P here is the midpoint of OA, and that the point Q here is the midpoint of AB. So what we can do before we go to the questions is find the position vector for each point in the system, because once we have the position vector for each point in the system, we can find any information relating to this vector triangle. And so that's the first thing we want to do. We want to deduce all the position vectors. So that's it. We are deducing the position vector of all the points. And firstly, we are given the position vector of A, that's OA, and we're also given the position vector of B. So we already have the position vector for each of these 2 points, A and B. So now we want the position vector of P and the position vector of Q. Now we're told that P is the midpoint of OA, and therefore simply the position vector of P, OP, is half of OA. That is, OP here is half of OA, and we know OA is 2 times A here, and so the position vector of P is half of 2A, which is A, and we can therefore show that vector OP on the diagram, and that's it. The vector OP is A, and since vector OA is 2A, it means that the vector PA is also A, and so that's it. OP, the vector OP, that's a position vector of P, is A, and the position vector of A is 2A. And we are also told that the vector OB is 2B, so we can go ahead and show that vector on the diagram as well. So that's it. Our vector OB is 2B. And now we want to find the position vector of Q. That's the vector OQ. And we're told that Q is the midpoint of AB. So we can use the formula for calculating the position vector of the midpoint of a line. And this is it. Since Q is the midpoint of AB, then the vector OQ, which is the position vector of Q, is half the sum of the position vectors of the endpoints of the line AB. And therefore, the vector OQ is half of OA plus OB. So we know OA is 2A here, and we know the vector OB is 2B here. And so we can substitute those values. And therefore, the vector OQ is half of 2A plus 2B. So that works out to A plus B, and so the vector OQ, that's a position vector of the point Q, is A plus B. So we can show that vector on the diagram, and that's it. The vector OQ is A plus B. Now that we have the position vector for each point, we can proceed to answering the question. We now have that OP is A, OA is 2A, OB is 2B, and OQ is A plus B. Now we can proceed to answering the questions. So this is it. We have OA equals 2A, OB equals 2B, OP equals A, and OQ equals A plus B. We have the position vector for each of the 4 points in this vector diagram. And so now we can proceed to answering the question. And the first thing we're required to find is the vector AB. And the vector AB is a displacement vector, and it can be expressed as the difference of these 2 position vectors, O times the last minus O times the first. In the displacement vector AB, B is the last and A is the first, and that displacement vector AB is given by O times the last is B, minus O times the first, where the first is A. The displacement vector AB is equal to OB minus OA. So we can substitute the values for OB here and substitute the values for OA here. And this is it. The vector AB is 2B minus 2A, and that's the answer for that part. We can also deduce the vector AB from the diagram, because to go from A to B, we will go negative 2A plus 2B. That's it. To go from A to B, we'll go negative 2A here to O, and then add 2B, and that's it. Negative 2A plus 2B. But using the formula, it is O times the last minus O times the first, and that's it. That's the answer. The displacement vector AB is 2B minus 2A. Next, we're asked to find the vector PQ. And again, this is the displacement vector PQ, and it's given as O times the last minus O times the first. And this is why it was so important for us to find the position vector for each point, because now that we have the position vector of P and we also have the position vector of Q, we can go ahead and find this displacement vector PQ in terms of the position vectors of the point P and the point Q. The displacement vector PQ is OQ minus OP. That's O times the last, which is Q, minus O times the first, which is P. Displacement vector PQ is OQ minus OP. So now we can substitute the values for OQ here and substitute the values for OP here. And this is it. OQ is A plus B. That's this. OQ is A plus B minus OP. OP is A. And when we do this calculation, A minus A leaves us with 0, and so we are left with B. And therefore, the vector PQ is the vector B. And we can show that on the diagram. That's the vector B. PQ is B. And the vector diagram here confirms what we have, because what we said is that the vector OQ is A plus B. And you can see, to go from O to Q, we could go A to here first and then add B here. So the vector triangle here confirms our calculation. OQ is A plus B, and we could go OP plus PQ to go from O to Q. So that's A plus B is equal to the vector A plus B here. So this vector triangle is confirming the information that we have. So let's move down now to part 3. Now part 3 is asking us to state two geometric relationships between the line segment OB and PQ. So what we need to do is compare the vector OB and the vector PQ so we can establish a relationship between them. Now usually the geometric relationship between lines in vectors that they are looking for is parallelism and also the ratio of lengths, or the relationship between the lengths. So what it is that we need to examine the relationship between these two lines in terms of whether or not they are parallel, and then also look at the ratio of the lines in terms of the length of these two lines. So let's look at that. Now what we have is that the vector OB is 2B and the vector PQ is B, and therefore from these two relationships, if OB is 2B here and PQ is B, it means that the vector OB is 2 times PQ, because PQ is B. So we are simply substituting this B here with the vector PQ, and so OB is equal to 2 times PQ, and this is a vector equation. This vector is a multiple of this vector, and it therefore means that the vector OB is parallel to the vector PQ, because when two vectors are parallel, one can be expressed as a multiple of the next. So we have deduced our first relationship between these two line segments. One vector is a multiple of the next, and therefore the line OB is parallel to the line PQ. OB and PQ are parallel. So that's our first geometric relationship. And as I said, we can look for a relationship in terms of the length. Now this is a vector equation, and we were able to deduce the parallelism between the line segments OB and PQ. Now we want to establish a relationship between the length of the lines, and so we need a scalar equation. To go from a vector equation to a scalar equation, we have to take the modulus of both sides of this vector equation, and this is it. Taking the modulus of both sides, we are able to remove the vector component, and when we do this, we see that the line segment OB is equal to 2 times the line segment PQ. This is now our scalar equation. By taking the modulus of both sides of this vector equation, we are able to remove the direction component from this vector equation, so that we only now have a scalar equation, which is a relationship between the length of the lines. And what this means is that the length of the line OB is equal to 2 times the length of the line PQ. And so we can write that as our second geometric relationship between the lines OB and PQ. And this is it. This means that the length of OB is twice the length of PQ. and that's it. We have our two geometric relationship between the lines. This vector equation gave us this parallel relationship, this parallel geometric relationship, and this scalar equation gave us the relationship in terms of the length of the lines, and that's the answer for part 3 of this question. Let's move down now to part B of question 11. In part B, we are given this matrix M 2, 1, 4, 3, and the first part wants us to calculate M to the minus 1, which is the inverse of the matrix M. Now the inverse of the matrix M is simply equal to 1 divided by the determinant of M multiplied by the adjoint of the matrix M. And I will proceed to do the calculation and explain as I go along. Now this is it. 1 divided by the determinant of M. Now the determinant of M is calculated right here. It is 2 times 3 minus 4 times 1. Now the determinant of M is calculated by multiplying this product and subtracting this product. That's the main diagonal product minus the second diagonal product. And so the determinant of M is equal to 2 times 3 minus 4 times 1, and that's how we calculate the determinant of M. Now the adjoint matrix of M is obtained by interchanging the elements of the main diagonal and changing the sign of the elements of the second diagonal, and therefore these two elements are interchanged, and hence we have 3 here and 2 here. These two elements are interchanged, and then we change the sign of these two elements, hence this becomes -1 here and this becomes -4 here. And that's how the adjoint matrix is formed. Interchange the main diagonal elements and change the signs of the second diagonal elements. And when we do this calculation, this becomes 1 divided by 2 multiplied by this matrix, because 2 times 3 is 6 and 4 times 1 is 4. 6 minus 4 is 2, and so we have 1 divided by 2 multiplied by the adjoint matrix. And all we need to do now is apply this half to each element inside this matrix here. And when we do that, we end up with this. M to the minus 1, that's the inverse matrix of M, is 1.5, -0.5, -2, 1. And that is because half of 3 is 1.5, half of -1 is -0.5, half of -4 is -2, and half of 2 is 1. And therefore this is M to the minus 1. And that's the answer for part 1. Let's move down now to part 2. Now what we have so far is M and M to the minus 1. That's the matrix M and the inverse of the matrix M. And now we are told in part 2 to show that M to the minus 1 multiplied by M is equal to I. Now I is the identity matrix 1, 0, 0, 1. That's called the identity matrix. And this identity matrix is equivalent to the number 1. And we're required to show here that the product of M to the minus 1 and M is equal to the identity matrix. So what we have to do is multiply this matrix here, that's M to the minus 1, by this matrix here, which is M. And we will show this calculation by going through the steps and show how this final 2 by 2 matrix will be obtained. These are the codes which show the rows and the columns we have to multiply to arrive at this final 2 by 2 matrix. When we multiply this 2 by 2 matrix by this 2 by 2 matrix, the result is going to be a 2 by 2 matrix. The first element here, R1C1, means we are multiplying this first row here by this first column here. So let's show that. And that's it. We are multiplying this row by this column, first row by first column, because this first element is in the first row and the first column. And so we multiply the first row, that's 1.5, -0.5, by this first column, which is 2, 4. And when we do the multiplication, we multiply along the row and down the column. So we are multiplying this first element in this row by this first element in this column, and then we multiply this second element in the row by this second element in the column. So let's show that calculation here, and that is it. The 1.5 is multiplied by 2, that's here, and then the -0.5 is multiplied by 4, -0.5 multiplied by 4. And when we do this calculation, the result is 1, because 1.5 multiplied by 2 is 3, and then this is -0.5 times 4, which is 2. So we're actually doing 3 minus 2, and 3 minus 2 is 1. This second element here is in the first row and the second column, and so we multiply this first row by this second column to get this element here. So let's show that. So we're multiplying this first row, which is this, by this second column to get this element, and we can again show the calculation for that element here. And so it's 1.5 multiplied by 1, that's what this is, and then negative 0.5 multiplied by 3, negative 0.5 multiplied by 3. Now 1.5 multiplied by 1 is 1.5, and we are subtracting 0.5 multiplied by 3, which is negative 1.5, and so we have 1.5 minus 1.5, and so the result here is 0. This element here is in the second row and the first column, and therefore we have to multiply this second row by this first column to get this element, which we'll end up with here. And so let's show the rows and column we have to multiply, and that's it. This second row multiplied by this first column will give us this element here. So let's show the calculation, and this is it. The negative 2 will multiply by the 2 here, that's it, and then this 1 will multiply by this 4. So we have negative 2 multiplied by 2, that's negative 4, and we have 1 multiplied by 4 is 4. So we actually have negative 4 plus 4, and that will work out to 0, and so that element is 0. Now this last element is in the second row and the second column, and so we have to multiply this second row by this second column. So let's show that, and this is it. We are multiplying this second row here by this second column here to get this element. And when we do that calculation, the result is this. Negative 2 multiplied by 1, that's what we have here, negative 2 multiplied by 1. And then 1 multiplied by 3, 1 multiplied by 3. Negative 2 multiplied by 1 is negative 2. 1 multiplied by 3 is 3. So we actually have negative 2 plus 3 here, which is 1. And so this element is 1. And therefore we have shown that m to the minus 1 multiplied by m is equal to 1, 0, 0, 1, which is the identity matrix. Therefore, we have proven that the product of the inverse of the matrix and the matrix is equal to the identity matrix. And that's the answer for that part of this question. Let's move down now to part 3. Now part 3 wants us to use the information we have to solve this matrices equation. Solving this matrices equation means we need to find the value for R, the value for S, the value for T, and the value for U. Now we must recognize that this matrix 2, 1, 4, 3 is actually the matrix M, and so we can show that. So what we actually have is that the matrix M multiplied by this matrix RSTU is equal to this matrix 2, 1, 4, minus 1. Now if the matrix M multiplied by this matrix is equal to this matrix, then it means that this matrix that we are trying to find can simply be equated to the inverse of M multiplied by this matrix here. But what I'll do is go through the steps and show how that result can be derived. Now the first thing we would do is multiply both sides of this matrices equation by the inverse of M, and that's it. We have multiplied both sides of this matrices equation by the inverse of M. Now we have just proven that the inverse of M multiplied by M is equal to the identity matrix, and so we know that the product of M to the minus 1 and M here would equal to the identity matrix, and so we can show that. And then now the identity matrix multiplied by a matrix is equal to the matrix, because the identity matrix is similar to the number 1. It's just like saying 1 multiplied by this matrix RSTU, and so the result of this multiplication would be RSTU, and that's the final result. This matrix RSTU will be equal to the inverse of M multiplied by this matrix on this side, and this is a standard result in matrices. If M multiplied by RSTU is equal to this matrix, then RSTU is equal to the inverse of the matrix M multiplied by this matrix, and we have just gone through the proof of this result. So all we need to do is do this calculation, bring our M to the minus 1 here and carry out this multiplication, and that will give us the elements RSTU. Let's show that calculation, and this is it. RSTU is equal to the inverse of the matrix M, that's here, the inverse of the matrix M, and we are multiplying that by this matrix here. And so again, I'll show the codes for this calculation, and we carry out the calculation to get our final result, which would be a 2 by 2 matrix, so we can identify the elements R, S, T, and U. Now the first element here is given the code R1C1, meaning we have to multiply the first row by the first column. This element is a first row, first column element, and so we have to multiply this first row by this first column to get this element. And let's show the result of that calculation. 1.5 multiplied by 2 is 3, and 0.5 multiplied by 4 is 2, and so this element is 3 minus 2, and the result of that 3 minus 2 is 1. And then this second element here is in the first row and the second column, hence it is called R1C2, meaning row 1 column 2. So we have to multiply this row 1 here by this column 2 here, and when we do that calculation, this is the result. 1.5 multiplied by 1 is 1.5, and then negative 0.5 multiplied by negative 1 is positive 0.5. And when we do this calculation, 1.5 plus 0.5, the result is 2, and therefore this element here is 2. This third element is in the second row and the first column, and therefore we have to multiply this second row by this first column to get this element here. Row 2 multiplied by column 1. That's row 2 multiplied by column 1. And when we do that calculation, this is the result. Negative 2 multiplied by 2 is negative 4, and 1 multiplied by 4 is positive 4. Negative 4 plus 4 is 0, and so the element here is 0. And then this final element is in the second row and the second column, and so we have to multiply this second row here by this second column here. And when we do that calculation, this is the result. Negative 2 multiplied by 1 is negative 2, and 1 multiplied by negative 1 is negative 1. And then negative 2 and negative 1 add to negative 3. And therefore, this is our resulting matrix. RSTU is equal to the matrix 1, 2, 0, negative 3. And therefore, R is equal to 1, S is equal to 2, T is equal to 0, and U is equal to negative 3. And so we can show our solution line. Solution is that R is equal to 1, S is equal to 2, T is equal to 0, and U is equal to negative 3. And that's the solution for this question. And that's the end of this question and the end of this production. As usual, I hope you learned a lot.
Daddy, you're recording mathematics the easy way for me?
Yes, Kai, but you have to be quiet. Remember, you have to be quiet when I'm recording this stuff, okay?
Yes, Daddy.
And I hope you'll continue to practice hard so you can pass your exams the easy way.
You have just seen the video solution for a special CXC question, but this is only one of the many different ways that these questions are written. All mathematical principles can only be fully understood by solving many questions, and so I always tell my students, more maths equals better maths, and if they study hard, they will pass easily. All the various types of CXC questions are covered in the Easy Way Mathematics Solution book, and you need to practice every single one of them. Other books in the series are the Easy Way Multiple Choice Specimen book, the Easy Way Unit 1 Cape Mathematics Solution book, and the Easy Way Account Solution book. Please feel free to contact me with your comments and queries at any time.